We're surrounded by mirrors, but the flat ones we have in our bathrooms, they're really just the beginning. The truth is, curved mirrors are kind of secretly shaping our world in all these ways we barely even notice, from the car you drive to the tools a dentist uses. So let's dive into the physics behind them, and we'll start with a few questions you've probably asked yourself before. First up, this absolute classic. You're on a road trip, you glance at your side view mirror, and you see that familiar warning. But why? Why does that mirror seem to shrink everything behind you? Well, it turns out it's a very deliberate design choice, and the physics behind it is surprisingly simple. Okay, and how about this one? We've all heard that a magnifying glass can start a fire, but a mirror? Come on, how can a shiny, reflective surface concentrate enough energy to actually burn something? Turns out, with just the right curve, it's not only possible, it's the exact principle behind some really powerful tools, like solar cookers. And of course, there's the funhouse effect. You can even try this right now. Go grab a shiny spoon and look at your reflection. On one side, you're upside down and all squished. Flip it over, and suddenly you're stretched out and wide. What is going on there? Well, the answers to all of these questions lie in understanding just two basic types of curved mirrors. So let's meet the two main characters in our story today, concave and convex mirrors. Now, their names might sound a little technical, but the core idea behind them is incredibly intuitive. It all just comes down to which way they curve and how that specific curve messes with rays of light. To really get our heads around this, let's use this brilliant little analogy. Just imagine sticking a whole row of pins into a flat piece of foam, okay? They all stand up perfectly straight, totally parallel to each other. Now, what do you think happens if we bend that foam? You see what happens if you bend the foam inward. And an easy way to remember this is that it goes in like a cave. The pins all start to point toward a single spot. They converge. That's a concave mirror. Now, if you bend the foam the other way, outward, like it's flexing a muscle, the pins spread apart. They diverge. That's a convex mirror. Converge versus diverge. That one simple difference is the key to, well, everything. So how can we actually predict the kinds of images these mirrors are going to form? I know, it seems super complex, but physicists have basically boiled it down to a kind of cheat sheet. We only need to trace the path of three specific, really easy rays of light to know exactly where an image will appear, how big it will be, and whether it's upside down or right side up. Okay, here are the three simple rules for a concave mirror. Rule number one, any ray of light that comes in parallel to the mirror centerline is always going to reflect through one single spot. We call that the focal point. Rule 2, the reverse is also true. A ray that passes through the focal point first is going to bounce off and travel out parallel. And rule 3, the easiest one, a ray that goes through the center of curvature. That's just the center of the giant sphere the mirror was sliced from. It's going to hit the mirror and reflect straight back on itself. That's it. By tracing just two of these three easy rays, we can predict exactly what the image is going to look like. All right, we've got the rules. Let's put them into practice. Let's see how these two types of mirrors, even though they're governed by the exact same laws of reflection, produce completely different views of the world. So let's start with a concave mirror, and we'll put an object kind of far away from it. Now, if we draw our easy rays from the very tip of that object, watch what happens. After bouncing off the mirror, the rays actually cross over and meet at a single point. And right there, where they meet, a focused image is formed. This is what we call a real image, and it's real because the light rays are physically converging at that spot. You could literally place a piece of paper right there and see the image projected onto it, all crisp and clear. This is pretty much how a movie projector works, and it's also why the image is often inverted or upside down. But wait, concave mirrors can do something totally different. Think about shaving mirrors or makeup mirrors. They're concave, but they show you an upright, magnified reflection. They don't turn you upside down. So what changes when you bring the object, in this case your face, really, really close to the mirror? Well, when an object gets closer than the focal point, the reflected rays start to spread out. They diverge. They never actually meet in the real world. But our brains are amazing, and they extend those lines backward, behind the mirror, to a point where they look like they came from. This is a virtual image. It looks like it's there, but you can't project it onto a screen because, well, the light rays aren't actually there. And this versatility is what makes concave mirrors so incredibly useful. Check out the pattern here. When the object is far away, you get a small, upside-down real image. As you move the object closer, that real image gets bigger and bigger. Then, right at the focal point, something wild happens. everything flips. The image suddenly becomes virtual, upright, and magnified. A concave mirror is like a multi-tool for light. Okay, so after all that complexity, the convex mirror is, well, it's refreshingly simple. Because its one and only job is to spread light out, its behavior is incredibly predictable. You could call it a one-trick pony, but you know what? It's a really, really useful trick. It doesn't matter where you put an object in front of a convex mirror. Far away, up close, anywhere in between, it makes no difference. The result is always the same. The image will always be virtual, appearing behind the mirror. It will always be erect or upright, and it will always be diminished or smaller than the real object. Always. And that consistency, that's its superpower. So we have the theory, we've got the rules. Now for the fun part. Let's connect all of this back to those puzzles we started with and see these principles at work all around us. And here it is, that famous phrase. You've seen it a million times. It's printed on pretty much every passenger side car mirror for a very, very good reason. And now we have all the tools to understand exactly what it means and why it's there. The whole reason objects look smaller and farther away is simply because that mirror isn't flat. It's a convex mirror. It bends outwards, spreading all those light rays apart. And, as we just saw, a convex mirror always creates a smaller, diminished image. So you might be thinking, why would engineers intentionally design a mirror that lies to you, that distorts reality? It's all about safety. Because that mirror shrinks the world, it can capture a much, much wider field of view than a flat mirror of the same size could. You can see more lanes of traffic, and you can significantly reduce your blind spot. The trade-off is, well, you just have to remember that things are actually closer than they look. Seriously, once you know what to look for, you will start seeing them everywhere. That shaving mirror that magnifies your face? Concave. The little mirror a dentist uses to get a big, clear view of a tooth? Concave. A satellite dish that focuses signals down onto a tiny receiver? You got it, that's a concave mirror. And those big, round security mirrors in the corner of a convenience store, giving you that wide view of all the aisles? That's a convex mirror doing its one perfect trick. So really, it all comes down to this. The simple physics of reflection has given us this incredible range of tools. By curving a surface one way, we can magnify and focus. And by curving it the other way, we get a wider, safer view of the world. It's all about just bending light in the right direction. Now, we focus today on reflection, but these same basic principles of focusing and spreading light also apply to refraction, which is the bending of light through materials like glass. So the next time you look through a pair of eyeglasses or a camera or a telescope, think about those invisible curves that are bending light to create the image you see. Thanks for joining me on this one.